Here is a combined summary of the 2 pages. This research explores the application of physics-informed neural networks, PINNs, to solve transport equation-based partial differential equations, PDEs. The primary objective is to analyze the impact of different activation functions incorporated within the PINN model on its predictive performance, specifically assessing the mean squared error, MSE, and mean absolute error, MA. The dataset used in the study consists of a varied set of input parameters related to strut diameter, unit cell size, and the corresponding yield stress values. The study focuses on evaluating the effectiveness of the PINN model and the significance of choosing appropriate activation functions for optimizing predictive performance in solving complex PDEs. The PINN model showcases exceptional generalization capabilities, indicating its capacity to avoid overfitting with the provided dataset. The research underscores the importance of striking a balance between performance and computational efficiency while selecting an activation function for specific real-world applications. The transport equation, a type of PDE, is formulated to model the underlying physical phenomena. The simplest form of the transport equation is represented by equation 1, where x is a unidimensional spatial variable and t is a time variable. The more general form of the transport equation is represented by equation 2, where U represents the mass density of a substance contained in a fluid and transported by the fluid itself. The principal equation is derived by imposing the law of conservation of mass, which can be subject to additional manipulations and solutions. The divergence theorem or Gauss-Green theorem is applied to reformulate the conservation of mass equation. The Cauchy problem, an initial value problem, is utilized to explore the evolution of mass density represented by the function U from its initial data. The visual representation of the transport equation, including surface and contour plots, provides valuable insights into the complex dynamics and spatial variations of the equation. The study aims to advance the understanding and potential adoption of PINN as an effective tool for solving challenging PDEs in diverse scientific and engineering domains. In the context of neural networks, activation functions play a pivotal role in enabling the learning of complex patterns from data. Most activation functions are nonlinear, as shown in Figure 3, which allows neural networks to capture intricate features present in datasets. Activation functions determine whether a neuron should fire or be activated based on the weighted sum of its inputs. The significance of nonlinear activation functions lies in their ability to go beyond merely learning linear and affine functions. Without nonlinear activation functions, neural networks would be limited to approximating linear combinations of input features, which is insufficient for capturing the intricate relationships and patterns that are common in real-world data. To illustrate this issue, consider a simple example of binary classification. If we attempt to classify points on a 2D plane into 2 classes using only a linear model, the decision boundary would be a straight line. However, many real-world datasets require decision boundaries that are more complex, possibly curved or irregular, to separate different classes accurately. Nonlinear activation functions like ReLU, sigmoid, or tanh introduce the required nonlinearity in the model, allowing it to learn intricate decision boundaries and patterns that linear functions cannot capture as shown in Figure 5. Figure 3 presents plots of various activation functions. The ReLU activation function is one of the most widely used activation functions in deep learning. It takes the input value and returns the input itself if it is positive, or 0 if the input is negative. This introduces nonlinearity and helps the network learn complex representations. However, ReLU can cause the dying ReLU problem where some neurons become inactive during training, leading to the loss of gradient flow and hampering learning. The tanh activation function maps the input to the range 1, 1. It is zero-centered, which mitigates the vanishing gradient problem associated with the sigmoid function. However, tanh is still susceptible to the vanishing gradient problem for extreme inputs. The sigmoid activation function maps the input to the range 0, 1. It is commonly used in the past for binary classification problems. However, sigmoid has vanishing gradient problems, making it less suitable for deep networks. The ELU activation function is another alternative to ReLU that addresses the dying ReLU problem. For negative inputs, it introduces an exponential component to produce negative values and allows non-zero gradients. The swish activation function combines the linearity of ReLU for positive inputs with the smoothness of the sigmoid function for negative inputs. This hybrid function is differentiable and has shown promising performance in some scenarios. This research paper presents a comprehensive comparison of decision boundaries obtained using various activation functions in the context of binary classification. The study employs a multi-layered perceptron (MLP) classifier with one hidden layer containing 10 neurons to investigate the learning capacity of neural networks under different activation functions. A synthetic dataset is used, comprising two distinct classes denoted by blue circles, Class 1, and red squares, Class 2, each consisting of 100 data points strategically distributed to challenge the classifiers in learning nonlinear decision boundaries effectively. The experimental data was obtained from the research conducted by Ozmi et al., who used fused deposition modeling, FDM, additive manufacturing, AM, technology on a Cube Pro machine to create lattice structure samples from acrylonitrile butadiene styrene, ABS, thermoplastic material. The lattice samples had a cubic shape with dimensions of 60 cubic millimeters and were designed using a combination of parameters in SolidWorks computer-aided design (CAD) software. These designs were then saved as STL files and imported into the Cube Pro software for the slicing process. The paper illustrates a 60 cubic millimeters tessellated body-centered cubic (BCC) lattice structure and a 20 millimeters BCC unit cell with a 5 millimeters strut diameter. The application area of lattice structures with BCC lattice strut-based designs is diverse, including aerospace engineering, where they are used for lightweight structural components, thermal management solutions, and load-bearing structures, as well as in medical implants, where their porous nature allows for enhanced osseointegration and nutrient diffusion. The mechanism used in this research work for synthetic data generation is polynomial regression and interpolation. Polynomial regression is a type of linear regression where the input features are transformed by raising them to certain powers. The polynomial features class from scikit-learn is employed to transform the input parameters into polynomial features of a specified degree. In this case, degree equals 3. This allows the model to capture more complex relationships between the inputs and the output. After fitting the polynomial regression model, the code proceeds with interpolation, generating a new dataset by interpolating the existing data points to create additional data points that lie between the original data points. This is achieved using the NP-interp function in NumPy, which performs linear interpolation. The original dataset contains a limited number of data points, but interpolation allows us to estimate the output parameter for a much larger number of input parameter values, thereby creating synthetic data as shown in Figure 7. Here is a combined summary of pages 7 and 8. The physics-informed neural network (PINN) model is employed to approximate the transport equation-based partial differential equations (PDEs), governing the yield stress of body-centered cubic (BCC) lattice structures. The model's architecture is implemented using TensorFlow and Keras libraries, consisting of multiple dense layers with tunable hidden units and various activation functions, including ELU, ReLU, swish, and sigmoid. The transport equation is incorporated into the loss function, which comprises both physics-informed and data-driven losses. The dataset is split into training and testing sets to evaluate the PINN model's performance using metrics such as mean squared error, MSE, and mean absolute error, MA. The results demonstrate that the PINN model effectively captures the underlying physics and accurately predicts the yield stress values. The comparison of 6 widely used activation functions reveals that all of them exhibit remarkably similar MSE and MA values, indicating consistent and precise predictive capabilities. The study highlights the critical role of activation functions in enabling the PINN model to capture nonlinear relationships and solve complex PDEs accurately. The obtained metric features, including MSE and MA values, are presented in Table 1, and the corresponding plots are shown in Figure 9. The findings suggest that any of the tested activation functions can be effectively employed, But computational efficiency should also be considered as a significant factor in selecting an appropriate activation function for large-scale or resource-intensive applications. The research provides an extensive investigation into the effectiveness of the PINN model for addressing transport equation-based PDEs, focusing on evaluating the impact of different activation functions within the PINN model and their influence on performance measures. The study underscores the PINN model's exceptional ability to capture the underlying physics and comprehend intricate data relationships, making it a promising approach for solving complex PDEs in various fields.